Hi guys, welcome to this lesson, Text and Test 6, chapter 3.9, page 125, 126. We're looking at Moivre's theorem today, which is a very important theorem in complex numbers, and in the context of the Leaving Cert there's nearly always a question about it, so it's an important topic for you for your exams. We're going to be looking at these questions 1, parts 1, 3 and 5, question 3 and question 9, part 1. So De Moivre's theorem is explained here on page 123 in the book. If you have a number in polar form and you want to raise it to the power of n, well, that's equivalent to just multiplying the arguments by n. Okay, and you'll notice there we haven't included a modulus here. We'll discuss problems with the modulus in a few minutes time. There's a proof there by induction, but proof by induction we haven't done. It's actually later on in this book that they talk about it, so I'm going to skip the proof and just assume that the theorem holds for the moment. We'll discuss the proof in sixth year. But what it says is, if you're asked to raise this number in polar form to the fourth power, well, that's the same as multiplying the arguments. So this becomes cos of 4 pi over 8 plus I sine 4 pi over 8. So that's just going to be cos 4 pi over 8 is pi over 2 plus I sine pi over 2. You can just go straight to your calculator if you make sure it's in radians mode, so it should say RAD up the top. Or if you prefer, pi radians is the same as 180 degrees. We discussed that before, but not discussed why. So that's the same as cos of 180 over 2 is 90 degrees plus I sine 90. Either way, well, actually let me show you this in radians. On the Casio here, if you want to change to radians, you go into setup. So that's shift and then the mode button. Option 4 there puts you in radians. You can see you get a little R up the top here. So I would say cos of pi over 2 is going to be 0 plus I sine of pi over 2 is 1 sine pi over 2 is 1, I times 1, and the answer here is just I. Okay, so this number raised to the fourth power is I. This number raised to the eighth power is going to be cos of 8 pi over 12 plus I sine 8 pi over 12. You don't even need to simplify that, even though that's going to be 2 pi over 3. But you can just go cos bracket 8 pi over 12 is going to be minus 0.5 plus I times sine of 8 pi over 12, and that's root 3 over 2. Change that for me? No. Okay, but if you look at root 3 over 2, you get the same number. So De Moivre's theorem, let's just say that's minus a half plus root 3 over 2I. This one here we have a negative index, which if you remember normally means, so x to the minus 1 is 1 over x, x to the minus 2 is 1 over x squared, x to the minus 3 is 1 over x cubed, etc. But with the negative indices we can still apply De Moivre with the same rule. That's going to become cos of minus 6 pi over 4 plus I sine minus 6 pi over 4. So that's going to be cos minus 6 pi over 4, which comes out as 0, plus I sine of minus 6 pi over 4, which is 1, and we get the answer I. So this number to the power of minus 6 is the same as this number to the power of 4. Now, question 3 gives us a number z, which is this number here, 3 cos pi over 10 plus I sine pi over 10. And they want us to find z to the power of 5 in Cartesian form. Well, to do that, you'd first say that that 5 is distributive over multiplication. That's the same as 3 to the power of 5 times the whole part in brackets to the power of 5. So that's our first step, and then we can apply to Moivre from here. 3 to the power of 5 is going to be 3 to the power of 5, 243. And that's going to be 243 cos 5 pi over 10 plus I sine 5 pi over 10, which is 243 cos pi over 2, which is cos 90. So cos 5 pi over 10, which is pi over 2. Sorry about that. 5 pi over 10 is going to be 0. And sine of 5 pi over 10, you can do it yourself in your calculator, is 1. So the answer there is going to be 243i is our answer. Question 9 part 1 gives us this number here. This is a very common Leaving Cert style question where they'll say, here's a number in Cartesian form, raise it to the power of 6. I mean, to multiply this by itself 6 times will take you an absolute age, so we won't try that. Even though you could try it as an approach, but if you were given it to the power of 12 or to the power of 15, it'll become extremely difficult. So we're going to use the Moivre, which means we need to be in polar form. So that number there is here, 3 minus 3 root 3i. The modulus of that number is going to be the square root of 3 squared plus root 3 squared, that's 9 plus 3, is root 12. The reference angle is going to be tan inverse, well, your opposite there is root 3 over your adjacent is 3 root 3 over 3. And the inverse tan of root 3 over 3, inverse tan root 3 over 3. Now we're in radians mode there. I would actually prefer to be in degrees mode, so let's go back to degrees and we'll say our inverse tan of root 3 over 3 is 30 degrees. Okay, so 30 degrees is our reference angle. Our argument, remember, is this angle here, which is 360. Take away 30. Is 330 degrees. So what they've asked us to do in 9 is to take the number root 12 cos 330 plus I sine 330 and raise that number to the power of 6. So our first step will be to distribute that 6 over both That's root 12 to the power 6. And then cos 330 to the power 6. Plus I sine 330. Then root 12 to the power 6 is 12 cubed. I don't know what that is. Root 12 to the power 6 is going to be 1728. So we're going to get ourselves 1728 times cos of 330 multiplied by 6 according to the Moivre's theorem, which is 1980 plus I sine 1980, and that's going to be 1728 cos 1980 is minus 1 plus I sine 1980 is 0. So the answer here is going to be minus 1728. Okay, in class we're going to work on questions 1 to 6, 8, finish question 9 and question 10. I'll see you tomorrow. Thank you.